professor here in the computer science department at NYU. I grew up in New Jersey, actually, in Piscataway. I don't know if any of those of you are from New Jersey. That's in central Jersey, near New Brunswick. And then I went to undergrad to study computer science, which is the same thing I'm doing now, in California at UC Berkeley, University of California, Berkeley. And following that, I came back to the East Coast, although living in California ruined me for life. And nonetheless, I moved to Boston. I did my PhD at MIT, also in computer science. And for the last 4 years, I've been here in New York City, working for the Cron Institute, teaching both at the undergraduate level and PhD level. I teach also data science in addition to computer science. So it's 9:30 and we'll get started. So the topic of today's course is going to be machine learning. And machine learning is something which it's a fun topic because it's something that really affects everything that we do today. So for those of you who have a mobile phone or whose parents have a mobile phone, you might have noticed that in the last 2-3 years, applications like Siri or Android's voice recognition are extremely good. So no matter what accent you have, you speak into it, it'll understand what you're saying, and moreover, it often comes up with a very good answer to your question. If you ask, how tall is Michael Jordan, it'll give you an answer back. So it understands your question, and it can find the answer and report it back to you. That's just one of many examples. I'll give you several others as we begin. So one example of something that you see every day is spam classification. Who uses Gmail? Okay. So Gmail, so you're very young, so you might not remember a time, almost certainly don't remember a time, let's say 15 years ago, when email actually was a real pain to use, because an overwhelmingly large fraction of emails that came into your inbox were garbage emails. People from, for example, right, here's an example of what I mean by a garbage or spam email. It's someone trying to sell a weight loss solution. And we would spend ages going through our inboxes trying to separate out and delete those spam emails. But about 10 years ago, this problem just disappeared completely. Because the industry, like places like Google, Microsoft, figured out a way to automatically classify emails into spam or not spam.
Which would go into the spam filter.
So it would go into, it's what you're called, what is called the spam filter. Would separate out into your spam folder versus your inbox. So spam emails would go into your spam folder, and your regular emails would go into your inbox. You got another question?
Yeah, also you get to see everything. Is it like option to see all the email? Like all the mail you have.
So you don't have to see everything is the point, right?
Yes, you can just see the inbox or the spam. But then it's like the option where you see both things.
Oh, okay, so there's some other ways of displaying email, but let's forget about those for the moment. So the real question is, how does this work? Does anyone have any idea how spam filters work? Yeah, in fact.
It uses things that people have marked as spam as guides to what a spam email would look like.
Very good. Okay, so that's a way of trying to get the labels, which is the first key point about machine learning. Machine learning uses data with labels in order to learn how to predict new things. So for spam filters, if no one ever said anything about emails that came into the inbox, then Google would know nothing. But every time there's a mistake, like for example, an email goes into the inbox when it should have gone to the spam folder or vice versa, there's an option to click not spam or spam and separate out those messages. And that's feedback that goes to the search engine in order to refine the way that it's classifying or filtering the emails. So that's the label. But what goes on behind the scenes? What information might the spam filter be using to distinguish a new email from spam or not spam?
I believe it looks for certain keywords that distinguish it.
So keywords, good. So what's an example of a keyword that might be indicative of a spam email?
Pills.
What's that word?
Pills.
Pills, yeah. Sale. Sale, not good.
Free.
What, free, good.
I was going to say free.
Anything else? Yep.
Discount.
Discount.
Coupons.
Coupons.
Like ads.
Ads.
This is blank.
Okay.
I'm sorry.
No, that's fine. Yep, say it again.
This is blank blank from marketing.
This is something something from.
Pay.
Pay. Yeah.
Lots of symbols.
Lots of symbols that aren't actually text. Good, very good. Okay, so we'll stop with those examples for now. What are some examples of words that might appear in non-spam emails? Someone who hasn't spoken yet today? Yeah.
Well, couldn't all those things appear in an email that's not like spam? So how does it distinguish if those words are in a, let's say, email that is not spam?
Great. So
it's maybe from someone else.
that's an excellent question. So his question, which I'll address in just 30 seconds, is, well, just because the word pay appears in an email doesn't mean that it's always going to be spam. Sometimes that word would appear in non-spam emails. We'll get back to that in a second. I want to hear a few examples of words that are more likely than not going to be in a non-spam email. In the back?
Your specific name, like dear, your specific name.
Dear David. My name is David, so Dear David. And that would be something that is specific to me. Yeah?
Sincerely.
Sincerely.
Stop.
Family. Good. So we'll stop with those. So let's get back to your question now. Well, clearly, there are some words that are more likely to be from spam emails and other words that are more likely to be from not spam emails. And if you think about approaches to try to do spam classification or filtering, the first approach that was taken about 20, 25 years ago was literally to come up with these lists of words. And if you see words from one list, send it to spam filter. If you see words from another list, send it to the not spam filter. And if there's anything in between, maybe you don't know. But that approach, as you can imagine, is very brittle. One reason why it's very brittle is because, well, first of all, words change over time. Right? The people who are sending spam emails learn to modify the words they use in order to try to get around the spam filters. The second reason is because, as you said, there are words that are just not clear what they're for. It's not necessarily the case that there's one word that's always going to be spam versus not spam. So a simple example of a rule that could be used to try to distinguish these two cases is the number of words. So suppose you have spam words and not spam words. If you get a new email and you look, what fraction of the words in the email are spam words? What fraction are not spam words? Or said differently, of the words that match to the two lists, which one has more of them? That would be one way of trying to get around this problem. But what spam classification algorithms do, and this is where machine learning comes in, is they actually learn a weight for every word. So rather than taking just an unweighted sum of the words to see how many of them are spam words versus non-spam words, every word is associated with a number. For example, pay might be associated with 2.3. Family might be associated with -4. Money might be associated with the number 5.4. And what's another non-spam word? David, which is my name, might be associated with the number -100. Right? Notice that I'm giving positive numbers to words that are indicative of spam emails and negative numbers to words that are indicative of not spam emails. And so when you take these sums of words you take a sum of the weights of the words that appear in an email, and then you can see is that weighted sum positive or negative? If it's positive, then you say it's a spam email. If it's negative, you say it's a not spam email. And the whole goal of machine learning is to tune those weights, using that implicit feedback that comes from people's labels in order to, as much as possible, classify past emails that should have been spam into spam, and emails that shouldn't have been spam into not spam. Question?
Well, can you also identify who's the sender? Like if it's from a company or something?
Very good point. So there are other features besides just words. One feature that's very important is who is sending the email, what is the IP address or location of the computer that it's sending from, and there are others as well. But I'm going to move on at this time to the next example, which is ranking. So most of you probably use Google or Bing or Yahoo search in your everyday, in your homework and other things. So here I'm just showing an example of a search query that I did cool looking cars. You'll see why that query is relevant to the rest of today's lecture in a moment. And there are billions of of web pages on the internet with the words cool looking cars somewhere in the web page. So if the search engine only looked to see what are the web pages with those words in it and tried to return those web pages, it would have no idea which ones are actually interesting or not interesting. So machine learning is used by all of the major search engines today to try to figure out which web pages should be ranked at the top versus on the bottom.
And never mind, I will go in this direction.
Okay, but I want to now ask the question that he answered earlier, which is where does the feedback come for ranking? And I'm going to, as much as possible, try to call people who haven't spoken yet. So you.
Like ratings, right?
Ratings.
A site, like at the, like something like sites have like the rating.
So where would you see the ratings? Like you would bookmark it, you mean?
Yeah, like bookmarking a site or like on a site like that, like the surveys that how much.
Oh, okay, so some sites have surveys on them. Sometimes you could bookmark pages and those bookmarks are shared with the search engine. So these are all ways of getting signals about the quality of the web pages. But nonetheless, we need some way of linking the quality of a web page to the search query that's being done. So how do we get that implicit feedback over there?
How often it's visited?
How often it's visited, but you're missing the connection to the query itself. Yeah, you back there.
When you click on the link to go there, it registers you clicking it and what you've searched.
Right.
And
So
associates them.
if after doing the search query cool-looking cars, I click on the best-looking car, that gives Google feedback that result is a good result for that search query. But that alone is not enough, because it could be I was fooled into thinking that was a good search result. I go to the web page and I realize it's not a good search result. Yeah?
How long you spend on that web page?
How long I spend on that web page is exactly where I was going with this. So I'll stop with the answers for that, because we've now sort of covered all the answers I was looking for this. So if I click on the second link, and then I immediately go back to Google and click on the first link, well, that'll tell Google that more likely than not, the second thing didn't satisfy my need for what I was looking for. And what's often used is what's called the last satisfied click. So Google will look at all of the clicks done, and it'll look to see what is the last one you clicked on before there's a 30-second time period that you do not return to Google. And it'll use that as an implicit signal that the last thing you clicked on is better than the first K things you clicked on. Now that signal is sometimes wrong, but nonetheless it's something which can be collected for trillions of search queries that have been done by everyone like you over time. So it's a way of getting a very noisy signal in abundance, and that's used to train the ranking algorithms. Yep.
Well, and also if you try looking on like the search bar, it shows like what the most rated thing that most people look up. For the search bar.
Up there you're saying?
Yeah.
Yes.
It also uses the ranking, but it also leaves funny searches.
So yeah, that's a very good point. There's another ranking going on here behind the scenes, which is the suggestions of search queries. That uses a slightly different approach, but also it's also something which can be trained in the same way. So if someone goes and then modifies their search query, so I don't like any of the search results, I go and I change my search query to say cool looking cars under 15K. That gives Google an implicit feedback that whenever someone types in cool looking cars, perhaps the search query that they thought they really needed was cool looking cars under 15K. And then the next person who comes along and types in that search query will get this suggestion. So here's another example, recommendation. So actually one of the high-level points I want to make here is that there's different types of machine learning problems. The first one we saw was classification, giving an input, trying to classify an email into spam or not spam. There are two classes there. The second example is ranking. Here there's not a class we're trying to put every document into, but rather we're trying to come up with a relative ordering of things. The third example is collaborative filtering. In collaborative filtering, we're trying to make suggestions or recommendations. So the example I want to work with here is from Netflix. Who's used Netflix? So it's a movie or video watching service, and about about the time that Netflix began, it gave suggestions. So it would look at what movies you've seen in the past, and it would give suggestions for movies that you might want to see. Now, in the very beginning, they used a very simple algorithm for doing suggestions. And then, about 8 years ago, when I was doing my PhD, Netflix decided that they should be able to improve their recommendation algorithm. So they released a data set that I'm showing to you right here, which had, they have tens of thousands of movies, for all of the movies that they own, and for all of the users, people like you, who've used Netflix in the past, they released this data set of ratings, of how people have rated movies in the past. So, this might be me, this might be you, this might be you, and for each movie that we've seen, there's a rating that we assign to that movie. And they publicly released this data set. Of course, they didn't give the names of the people. In fact, they even went a step further. They didn't even give the names of the movies. They kept that secret. But they asked the machine learning community, could you try to fill in the dots? For example, what do you think this rating is? Or what do you think that rating is? So let's do a quick experiment here. What number do you think this is? And why? Yeah, the back.
4 or 5, because everybody else rated it 4 or 5.
Okay, that's an excellent observation. Other people seem to like this movie, so maybe it's 4 or 5. Suppose that this number was 5. Then what do we think this number would be?
Lower, like 1 or 2. They might not have the same taste.
They may not have the same taste as this person, because if this was 5, notice that this user rated the same movie as this user a much lower value. So perhaps their taste is different. Yet if we look at this user over here, this user rated this movie a very similar number to this user. And so perhaps it's more likely that this number is 4 than 5, because of recognizing those connections between users. Notice we did all of that without knowing anything about what the movies actually were. So here's what happened. Netflix put $1 million on this problem. They said, whoever can come up with the best algorithm to fill in these question marks gets $1 million. This was 7 or 8 years ago. Inflation has been non-trivial since then, so $1 million, it's a lot of money. So, as you can imagine, this got the machine learning community really interested in this problem, and it really kickstarted a lot of research into how to do collaborative filtering. And the algorithms that people came up with are not dissimilar to the ones that we were just talking about. The way they work is to try to find some low-dimensional representation of movies and users that can try to generalize across the missing entries, recognizing that some movies might be similar to each other because the users rated those movies similarly, and some users might be similar to each other because the users rated the movies similarly, or vice versa. So, so the algorithms that you're using today, so the algorithms that are being used today to recommend movies to you are in fact based on machine learning algorithms, based on the feedback that Netflix gets from other users watching other movies that are common to the movies that you've watched. So here's the final example. It has to do with clustering from data. Actually, there's one more example after this. This is an example of what's called unsupervised machine learning, because there's no specific task we're trying to solve. We're not trying to predict something, we're not trying to rank something, we're not trying to recommend something. Rather, we're trying to understand data. And I don't know if any of you have been reading the New York Times lately, but data science is a big thing these days. And all of the major companies are scrambling to hire data scientists who their job is to try to make sense of data, draw inferences from data. this is an example of a data science problem. We look at this data and we want to ask questions of it. For example, how many clusters are there? Any ideas? Actually, what I think I'll do is I'm going to ask for a suggestion. Who thinks there are 3 clusters here? Raise your hand. Who thinks there are 4 clusters here? Raise your hand. Who thinks there are 5 clusters here? Raise your hand. And who thinks there are 6? All right, so this is something that humans do, well, I don't know if you're right or wrong, but at least almost all of you thought that there were 5 clusters. So, right or wrong, it was relatively unambiguous. You could look at this data and you think there are 5 clusters. You think that there's something meaningful about all of these data points being near each other. You think there's something meaningful about all of those data points being near each other. So this is something that you can do because you have some implicit idea in your mind that if there's space between data points with very few data points, then it probably indicates a separation between those data points. And that's why you recognize that this might be a different cluster from that one. But now try imagining doing this not in 2 dimensions, but 10,000 dimensions. Okay? Or if you want to think about the 3-dimensional version, we're in this room and there's data filling up the different spaces of this room. Okay, that would be 3 dimensions, and 10,000 dimensions, of course, you can't even imagine or visualize in your head. So the task of trying to discover those clusters in very high dimensions is a hard problem for humans to solve. But that's exactly the type of thing that machine learning algorithms can attempt to do. And there's a whole class of algorithms for clustering, which really are being widely used across computational biology, across industry, technology industry, across sciences like in economics and other fields, to really try to make sense of data. So here's one cool example of trying to make sense of data, and it has to do with visualizing data. So here we're going to try to take images of faces and place them automatically onto a plane. So the algorithm which was done, which I won't describe in detail today, figured out, so each of those dots represents a face. I'm only showing you some of the faces, but you can see that just by looking at the raw images, it figured out that there was some underlying structure in images. So in particular, it recognized that one notion of structure is the angle on which the face is. So if you look on the left-hand side, you'll see people who are, actually I think it's, so you'll see people on the left-hand side whose faces are a little tilted to the left. On the right-hand side, you see faces who are straight ahead. You see people smiling if you go to the top, and doing sort of weird facial expressions to the left. So this type of embedding was figured out automatically on faces. I think I'm going to jump quickly to another example, which is even more compelling, which is embedding of words. So here what we've done is we've tried to automatically group together words into semantically related things. So for example, you see that southwest, northwest are all grouped together. East, south, west are also grouped together, but they're close by these other directional words. June, August, January, February, March are all grouped together. USA, Hong Kong, Philippines, Israel, all the countries are grouped together over here. So in this way, we've discovered some meaning of words, grouping together words that are semantically related. But the input to this was just documents. So for example, the input might have been Wikipedia. Input Wikipedia, output this representation, which automatically discovered which words are semantically related to each other. Any idea how that might have been done? Okay.
How many times the Wikipedia pages of those link to the Wikipedia pages of things near it?
Well, these words don't even necessarily appear as a Wikipedia page by themselves. Like there might be a Wikipedia page for March, but I'm not aware of it. So the link structure, although it's a great idea and is used across a large number of different problems, wasn't used for this specifically.
How many times did it appear in lists together? Like, signal stuff you use the less.
Yes, so that's also a good suggestion. And actually a lot of information in Wikipedia can be derived automatically from lists that are found on the web for related concepts. But this is something which is much simpler. It doesn't use the structure of web pages, doesn't use the structure of the links. Yeah?
Wait, I was just gonna say, like, sometimes they have like a larger page that like has all the smaller ones linked to it.
So again, another suggestion of the link structure. Yep.
My guess is that they're pulling the nouns out and figuring out what words are surrounding them and connecting them into similar surrounding words.
Okay, so you're getting a little bit closer to what I'm thinking about. And the suggestion he's starting to get us toward is looking at context of words. Does anyone want to expand on that a little bit? Yep.
If words are used in like the same context, like if like the United States is used in a more context, like a country relationship, and like Japan is also used like that, so they use it in the same context.
Excellent. That's exactly what I was looking for. So what's an example of a sentence involving the word United States? Anyone? Anyone who hasn't spoken yet today?
Freedom.
Excuse me?
Freedom.
Freedom?
Yeah.
Give me a whole sentence.
USA is, I can't think of one right now.
USA is a country, okay? And one can also imagine another sentence saying Japan is a country. Alright, now if we look at those two sentences, is a country is to the right-hand side of the United States and is to the right-hand side of Japan. So if you look at the contexts of, that is a word surrounding a given word in a large corpus of documents, we can recognize that words might be similar to one another if they have the same or similar contexts. And that is the type of information which is used to actually discover these word embeddings. And so really one of the things I want you to take home from this is that machine learning can be applied in many clever ways. It doesn't have to be as simple as someone going and labeling an email as spam or not spam and giving explicit feedback. It could also be used from a lot of implicit signals. And a lot of what makes this field so interesting and fun is because it leaves room for creativity, for thinking about what are ways to get information on the things you're trying to figure out. So I heard about 10 different suggestions from everyone of really good ideas for how you could do this. And each one of those would give a different type of embedding. But that's where creativity comes in. And I find it to be a real fun field because of that. So what I'm going to do now is I'm going to just summarize some of these applications, and we're going to talk about some algorithms. And I'll go into a little bit more detail about how a very specific machine learning problem is solved. So just to summarize, machine learning is being used widely to solve tons of problems that you might care about. Things like speech recognition, machine translation, going from English to French, computer vision to try to understand what is in an image, to figure out if you upload an image to Facebook, who are the people in the images? Are they your friends? Can you automatically tag each face with a name? Robot control, so self-driving cars today are using machine learning to try to figure out, to do computer vision, to try to figure out what are objects in the road, should you stop, are you steering in the right direction, and so on. And it's a field that's really changed in the last 15 years because, number one, there's a huge amount of data that's now available to do machine learning, and people are being very creative about the uses of those data, like we just talked about in the previous example. Number two, computers are getting faster and faster, and these algorithms actually take a lot of compute power. And so that's been really helping. I don't know if any of you play video games, but video games are powered by GPUs, or graphics processing units. It turns out that machine learning algorithms are also running on GPUs today, because GPUs have so many different cores. They have thousands, the best GPUs have hundreds or thousands of cores that you can do a ton of parallel processing on them. So rather than just using it for playing games, you can also use it for solving important problems in computational biology, for example. So let's now jump into our first example of machine learning. And here I want to really illustrate a couple of key points to you about the types of things you have to think about in the back of your mind when you're trying to tackle a machine learning problem. So this is going to be a really simple task, something which is called regression. The input is going to be denoted here by the x-axis. So the input will be something like this 0.5 will be an example of an input. And the goal of the algorithm is to predict y, which is here denoted on the y-axis. So if I input 0.5, I want the output to be 0. If I input 0.25, I want the output to be 1. If I input 0.75, I want the output to be 0. Okay? So the goal is to go from x to y, and your training data corresponds to those blue points. The ground truth is what I'm drawing here as the green sinusoidal line. Okay? So that green curve is not known. I'm only showing it to you so that you have an idea of what the ground truth values should be. All that's observed to the machine learning algorithm are these blue points. And our goal is, given those blue points, can we figure out how to map a new point that's never been seen before? For example, if I was to give you this point, this location, if I gave you that location, then we know what the value for y should be. We might predict whatever that blue value was, that blue point up there, so 0.5 or so, or 0.3. But if I give you something else, like right here, something that's never been seen before, you'd have to guess what to do. And so one guess would be, well, look at the nearest 2 points, that blue point and that blue point, and maybe if we're asking you to predict here, you can look at the 2 nearest blue points and predict maybe the average of their values. So maybe you would predict something like that. But let's try to figure out how to do that more generally. So the first question I want to ask you is, how can we come up with a way of fitting a function? So given these blue points, we're going to try to find a function which maps x to y. And the first task that one has to solve in machine learning is to choose a function family. To think about what it would be a general class of functions that one could try to fit. So one example might be letting that function be a degree m polynomial. So by a polynomial, I mean the following thing. Y is equal to x.
And it's going to consider other things.
Well, you consider more and more complex functions, but the green curve is just me telling you this is how the data was actually generated. It was generated by looking to see for a given x what the corresponding point is on the green curve, and then perturbing it by adding a little bit of noise. But all you observe, all the machine learning algorithm observes are the blue points. Here's the analogy is as follows. Gmail only observes, or I'll stick with the Google example, it only observes that implicit feedback given to you when you're searching, right? The last satisfied click. That last satisfied click is sometimes wrong, right? Sometimes the first thing you looked at gave you the interesting information, you just kept on going because you had time on your hands. In the same way, the fact that those blue points are not directly on the green line is from also noise in the process.
So you're saying that, given any data set, before you find a function that best fits that data set, you need to have a model in mind to be able to fine tune it.
That's exactly right. So typically what we do is we first think what is a class of functions or models that we want to choose from, and then we try to find the best function from that class of functions. So the example I give here is first we decide we're going to search over all degree 1 polynomials. And then we get to tune it. Like we can say, okay, we get to choose this constant value, we get to choose the multiplier on x. A different choice would be to say, oh, we're going to search over all degree 2 polynomials, or all degree 3 polynomials, all degree 4 polynomials, and so on. And each one of those choices corresponds to a different complexity of a function. And those have trade-offs. So for example, if you look at the best degree 0 polynomial here, it's going to be that straight line. If you look at the best degree 1 polynomial, it'll be that. If you look at the best degree 3 polynomial, it'll look like this. Best degree 9 polynomial looks like this. Right? So when I say best, I mean I've searched over all degree 3 polynomials, meaning I've searched over all of these coefficients, and just to be specific, for degree 3, the choices are as follows. Okay? This is an example of a degree 3 polynomial, and the things that we get to choose are A, B, C, and D. Okay? So here I'm plotting for you the red curve is having chosen the best A, B, C, and D in order to get the red curve to touch as many of the blue points as possible. But there's going to be a trade-off here. What's your question? There's going to be a trade-off here because as we choose higher and higher dimensional polynomials, we're going to fit the blue curve better. We're going to fit the blue points better. So notice that once you go to degree 9, we can exactly fit all of the training data. Given any input x, which has been seen in the training data, we'll be able to perfectly predict what its value was. But this ignores the fact that there's noise in the process. And in doing so, what we're doing is we're fitting the noisy data. And if you were to give a new data point, let's say right here, and predict its value, you're going to predict that, which, and this is where now we use the green curve, we know that actually that's very far from the true value you should be predicting, which is down here. Yeah, you have a question? You.
So is there a way of by looking at all the data sets instead of eyeballing and saying that one looks better than that, is there a way to rank how good the model fits it? And if given the spaces between all the points, if you're able to register that going from here to here, there's a space, but as you see in the degree 9 one, it makes this big jump from the first point to the second. And saying, well, we want it to be continuous to the next point, so we want it to be along these lines, so how much is it deviating from it, and is that going to affect the value of it really not being the best fit for data?
So the suggestion, I'm going to turn your suggestion into a statement. The suggestion which is given is, well, maybe there should be some preferences here. Maybe we should, all else being equal, prefer functions which don't have these big jumps in them. Because big jumps imply greater complexity. Greater complexity means that maybe you're more likely to overfit your training data. So, indeed, the second problem that needs to be solved in machine learning, the first one is to choose your function class. The second one is to decide what is your notion of complexity and how can you try to prevent yourself from overfitting. Now, to formalize the notion of what I mean by overfitting, I want to show you what's called a learning curve. Here what we're doing is on this axis over here, we're changing the model complexity. And for us, we're going to measure model complexity with the degree of the polynomial that we're fitting. On the y-axis over here, I'm showing you a notion of error. And that's computed using your training data. So for us, we're going to use what's called squared loss. Our training data consists of pairs of data points. So it's going to be something like, I just want to know what are all those blue points. Can someone read off to me what the coordinates might be for those blue points?
0,
0, comma 0.5.
Yeah.
What else?
1, 0.3.
It's hard to read off the slide. Yeah?
2 comma 1.
Okay, 2 comma 1. Okay, I'm going to stop there. Oh, no, there's no 2.
It only goes to 1.
It only goes to 1.
Well, yeah, but
Which ones?
I thought we were dividing the 0 to 1 into 10 spaces.
Oh, I see. I see.
It's
No, I
easier to
wasn't
say.
doing that. So then that would be 0.2 comma 0.1 or something. Okay, anyway, so this is your training data. I'm going to call this D. Alright, so that's your training data. These are the blue points. We're going to measure error by summing over your training data, summing from I equals 1 to, how many data points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 data points. So summing from I equals 1 to 10 of the yi, which is the y coordinate position for the ith data point, minus whatever the function predicts given as input the xi coordinate. And we're then going to square this. So this is what's called squared loss. And this measures the discrepancy between the prediction of the function, which is this quantity, and the observed value of the data point, which is this quantity. And we can evaluate what this is for different functions of different complexity. So we notice when you have a degree 0 polynomial, that's that one over there, on average, that red line is roughly almost distance 0.5 on average from the blue data points. Okay? There's a big distance from the red line to the blue points. And as the degree of the polynomial gets bigger and bigger and bigger, up to degree 9, when you look at the degree 9 polynomial, that red line hits all the blue points. So the squared error is 0 because yi is equal to f of xi for all 10 data points. Yep?
Why do you square the error?
Ah, great question. So I put a square here, and the answer is it's arbitrary. So but it raises a very good point. There's one more decision that needs to be made by the algorithm designer, which is you and me, which is how do we want to measure error? And that depends on the task you care about. So this is a choice that we get to make. Here I chose it to be squared. We could have made it cubed or to the power of 4, or maybe we even could have chosen just absolute value instead of squared. Well, almost certainly what we want is we want something here which is always non-negative. Some measure, so that, and we want something that's non-negative and is equal to 0 if yi is equal to f of xi. This is called the loss function. It's something that you get to choose. So what I'm showing you here is how that loss, or the error, decreases as you increase your model complexity. But there's something else you need to be thinking about. Not just the model error, but the test error. So the test error you should think of as, suppose that there's another data set. For example, suppose that, see those blue points? Suppose I split those blue points in 2. Okay? So you have 5 points and another 5 points. We use the first 5 points to evaluate this blue curve and to fix the polynomial. So we use the first 5 points to choose those red lines. That means the second set of 5 points to evaluate the squared error using the red curve that was fit using the first 5 points. And what you'll find is that, so that's where that green curve comes in. By looking at the discrepancy from the green curve to the red curve, that's going to be closely approximated by the error of that held out set of data points. And what you'll see is that as the models get more and more complex, that test error, or the error on unseen data, not used during training, starts to get bigger and bigger. And exactly what you're saying, as your model gets more and more complex, as it starts doing these really weird jumps, the test error starts growing. And so we need to start thinking about how to measure test error. And one way to do so is by what I was alluding to a moment ago, which is having a held out set. So you take your training data, you split it in 2, you use one half of it for learning your function, another half to evaluate how well you generalize into new data. And then you stop once you see that red curve going up. So the blue curve is always going to go down, but you notice the red curve starts going up here, so you might stop, I don't know, maybe the best place to stop would be here, degree 3 polynomial. And that's the answer. You use this degree 3 polynomial going into the future. So there are a number of key challenges when you do machine learning, which need to be solved. First, How do you choose a hypothesis space? So by hypothesis space here I meant class of functions. That's a choice that we need to make. If we had some idea, that if we knew something about the data, if we knew that that the data was generated from a sinusoidal function, then we might choose the hypothesis class to be the set of sinusoid and cosine functions. But typically you don't know anything about the data. So you have to guess what is a good class of functions. Well, we know that polynomials can fit almost anything. So polynomials, as long as your data is smooth in some way, would be a good choice of hypothesis class. The second decision that needs to be made is how do we measure accuracy on your unseen training data? Now, I suggested one way of doing so, which is to split your data in two and to use that held out set to evaluate how well you'd be doing on new data. But a second approach that's often taken is simply to have a bias towards as simple a hypothesis as possible. And this is getting back to your point. So this goes by the name of Occam. Occam was a monk from, I can't remember, 16th century maybe, whose philosophy was choose the hypothesis which fits your data and is as simple as possible. And this is a philosophy which really guides the development of machine learning algorithms. Whenever you have a choice between different hypothesis classes that fit your data equally well or close to equally well, choose the simplest looking one. So for polynomials, the simplest looking one would be the one which has the lowest degree. As the degree of the polynomial grows, you get more and more spikes and jumps, and the polynomials look more and more complex. And the third problem is an algorithmic problem. This is where computer science comes in. How do we find the best hypothesis? So one thing which I completely hid from you is how do we find this red curve? Right? We chose that we wanted to find a degree 3 polynomial, but if you look at degree 3 polynomials, there are 4 numbers that need to be chosen, A, B, C, and D. Given those 10 blue data points, how do you find the values of A, B, C, and D in order to minimize this quantity? That's an algorithmic task, or a mathematical task. And it's one that you have to come up with an approach to try to solve. And I'm not going to tell you how to solve that in today's lecture. But let me just allude to the fact that you do know how to solve that problem in some simple examples. The simplest example that you might have seen is when you have 2 data points. Okay? Suppose that this was your data. Okay? If that was your data, and I told you find a degree 1 polynomial to fit this data, well, this is something that everyone can do, right? Because a degree 1 polynomial is a line. And we know, given 2 data points, there's a unique line that goes between them and minimizes the reconstruction error. And then we could look to see, well, what is the y-intercept of that line and what is the x-intercept of that line, and from those 2 values, figure out what should A and B be for that line. Right, so that gives you an example of how you could try to pull out what the values of A and B must be. Here, I'm talking about the following: y equals ax plus b. Right, let's just do that. So we would look to see, well, when x is equal to 0, what is this value? That tells us b. When y is 0, what is x? And you can solve for a from that. Okay, so what I want to do in the remaining 10 minutes is introduce you to one concept in computer science, which is called recursion. And I want to teach you that concept through the lens of learning decision trees. So here's an example of a decision tree learning problem. We have this data, and this is now where we come back to the cars example. This data is about cars. Every row in this table is a car, and we know for that car whether its miles per gallon is good or bad. Like, is it over 30 miles per gallon? If so, we call it good. Otherwise, we call it bad. And And this is the thing we want to be able to predict. And we want to be able to predict it from all of the other columns, like how many cylinders is the car, is the horsepower high or low, is the car heavy or not, does it accelerate well or not, what year was the car built, and probably most importantly, what country was the car built in. So our goal here is to learn a function that can map from X to Y. And we have as examples training data from previous cars where we know the ground truth Y. We want to learn a function to map from X to Y so that if I give you a new car and I tell you some things about it, what year it was built, the number of cylinders it has, and so on, you can predict whether it's going to have good mileage or bad mileage. So the way that we're going to do this is to learn a decision tree. And a decision tree looks something like this. A decision tree will look at one of the features. So one of these columns corresponds to a feature. So in the previous examples we looked at, there was only a single feature, X. Now there are multiple features. So the number of cylinders is a feature, the year of the car is a feature, and so on. And a decision tree will learn to look at one feature and then branch based on its value. And at the very end, when it gets to the bottom, it predicts something, bad or good. So for example, it might first look at the number of cylinders. If the number of cylinders is 3, it might say, okay, that's enough information. I don't need to know anything else. It has good miles per gallon. If the number of cylinders is 4, it might say, oh, that's not quite enough information. I need to look at some other piece of the data. Here we'll look at the maker. If the maker is European, we'll say it has good mileage. If the maker is American, we'll say it has bad mileage. And this is an example of a decision tree. And our goal is, given the data, to try to find a decision tree which predicts the data well. Yep?
So we're not going to, you would not prefer turning this into like a 4-degree thing where you find a function based on it. You're going to turn this into like a logic tree basically.
Exactly. So this gets, one of the reasons I wanted to show you this in contrast to the previous example is because this is where choosing a hypothesis class comes in. For the previous problem of regression, we chose a hypothesis class to be degree m polynomials. Here, we're going to choose a different hypothesis class. The hypothesis class is decision trees. It's just a different choice. One reason why you wouldn't want to use a degree m polynomial is because these features aren't continuous. They're discrete. So it's not clear what it would mean to square the maker of a car, for example. The second reason is because the output isn't a continuous value, but a discrete value. We're trying to predict bad versus good. And that's the second reason why why we might want to choose a different hypothesis class. So again, there's a choice to be made. Okay, so just to finalize, the way decision trees work, the way that prediction is done using decision tree, each internal node tests some feature or attribute of the data point, and then it branches based on whatever the value is, and finally when you get to a leaf, you make a prediction of what the class is. So this hypothesis class has one nice example property, which is that it's human interpretable. So often, some machine learning algorithms are a big black box. And they might get very good predictive accuracy, but if you want to explain to someone why it works, it's very hard to do. This has the property that it's pretty easy to understand, which is nice. But not all decision trees are equal. So, for example, these are two different decision trees that actually compute the same function. You notice that if A and B are both true, then you traverse that left two branches, you predict plus here. If A and B are both true, and let's say C is false, here B is true, you go this way, C is false, you go this way, A is true, you go this way, notice that you predict plus still. So these two, you could convince yourself that these two compute the exact same function. But this one has depth 2 and this one has depth 3. So we have to, remember I told you one of the things we need to solve when tackling a machine learning algorithm is choosing how to bias ourselves to simpler functions. Here we biased ourselves to simpler functions. We used Occam's razor to prefer lower degree polynomials. When learning decision trees, we're going to bias ourselves to simpler functions by preferring decision trees which are low depth. So that's to say we would prefer this one to that one because this one is a simpler tree than this one. And again, that's a choice that we make, and we make that choice in order to try to prevent ourselves from overfitting the training data. As the tree gets deeper and deeper, you'll be able to fit any set of data points and predict those perfectly, but you won't generalize to new data. This finishes at 10:30, is that right? Okay. So I want to show you an example of trying to learn a decision tree. I've used a programming language called Python to learn a decision tree for predicting diabetes in an Indian population in the United States, near Arizona. This is a population that's been studied since 1965. People have been tracked over a long period of time, and various properties of them have been measured, such as their body mass index, their blood pressure, the amount of blood sugar that they have, and so on. And then over time, we discover who gets type 2 diabetes and who doesn't get type 2 diabetes. And our goal is to learn a decision tree to try to distinguish between these groups of people. So what I did here is I loaded in the data into two different tables. X is an array of the original data, and Y is the set of values, the ground truth, whether the person gets diabetes or not. And I'm just going to visualize it for you here. So here's a visualization of X. I'm going to do this, it'll be easier to read. So here I'm just showing you the data. The first column corresponds to the number, so this is for women. We're only going to predict for women. The first column is the number of times that the woman has gotten pregnant. The second column is their glucose concentration. The third column is their blood pressure, and so on. So this is the raw data. And in addition, we know the ground truth of whether the woman got type 2 diabetes a few years later or not. So for the first row, that's in Y1, and it's 0. The second row, it's in Y2, and that's 1. So Y is a vector which encodes the ground truth, whether a corresponding row is diabetic or not. Now what I'm going to do is I'm simply going to, these lines right here, I'm using an off-the-shelf machine learning algorithm to try to fit the data. So that's what this line does. It says, fit a decision tree classifier to try to map X to Y. X has the data, Y are the labels. And I hit run. Oops, I hit run. And it takes some time to run. At some point it'll output something. Let's wait a few seconds. Okay, so it just finished running. It output the decision tree classifier. Now what I'm going to do is I'm going to try to visualize it. So here I visualized the output, and this is the decision tree that was learned by the algorithm. It first decides to look at the glucose concentration of the person. If the glucose concentration is larger than 127, then it means the person is glucose is very tightly tied to diabetes. So if someone has high glucose, it's not surprising. You should think that they're very likely to get diabetes. So here you branch to the right if they do have high glucose. And then you look at their body mass index. Again, all of these things were automatically learned by the decision tree learning algorithm. If the body mass index is high, you go to the right, and you look at the glucose levels again. If the glucose levels are even higher, say higher than 157, you go over here. And every data point that reaches here has glucose above 157 and body mass index above 30. And you notice down here are the values. You see that 80 of those people actually do get diabetes and 12 do not. Well, if you went the other direction, if someone had low glucose and low body mass index, then 121 of them do not get diabetes and 1 does. So I just wanted to illustrate to you briefly how with just a few lines of programming, one can read in data and run a machine learning algorithm. So I'm going to now finish with the following. Oops. Here we go. So machine learning uses a lot of math. I hope I illustrated that point with some of the functions that we talked about. It uses calculus, it uses statistics, and it uses linear algebra. So these are things, some of them, like calculus, you might start learning about in the later stages of high school. Others are topics that you might learn about in college. So hold your question for a moment.
Sorry.
If you're interested in machine learning, you might consider when you go to college to study computer science. Computer science is really at the foundation of how one does machine learning because it tackles the algorithmic task of, for example, given the data, how do you find a good decision tree which fits the data well? I didn't give you the algorithm today, but you can try to learn about that when you go home. Or given data and a function, how do you fit the values, the parameters, in order to fit the data well? Those are all algorithmic tasks which you would learn in computer science. Now in the meantime, you're in high school now, but if you get free time this summer, you might already want to try to learn some machine learning. I taught myself machine learning in high school when I was I think a junior in high school. But I just got a book from the library and started reading it. But today it's a lot easier. There are actually websites that teach machine learning at a level that probably you could understand using the mathematics that you already know. So in particular, I suggest going to this website called Coursera, coursera.org/course/ml, where there's a free machine learning class that you can just take online. You can watch the lectures, and they have homework assignments that you can do to teach yourself and practice the machine learning algorithms. Now, I imagine most of you don't know how to program, and so a second thing you can learn to do is learn how to code. And there's another website called Code Academy that you can go to, codeacademy.com, where they'll walk you through learning how to program using, for example, a language called Python or JavaScript, or even you could learn how to make web pages if you want. Again, this is freely available. If you have some free time this summer, you might play around with Code Academy to learn how to program, and you might go to Coursera to try to learn something about machine learning. So that's it. There was a question in the back.
Yeah, you